Hi students, in this session I am going to discuss the assertion and reasoning type questions from the chapter haloalkanes and haloarenes. And before we saw MCQ type of questions in this chapter, okay, I'll give the link in the description box. See, some of the students know they find it to gain marks in assertion and reason type of questions because all the options are very closely related, and if you do a minute mistake you will lose marks, okay. But if you are very strong in the concept and if you analyze the questions in depth logically, then it is very easy to score marks, okay. So here both assertion and reasoning will be given. Here in option A, both assertion and reasoning are true and the reason is the correct explanation of the assertion, okay. So this is option A. If both assertion and reasoning are true but reason is not the perfect explanation of the assertion, then you have to select option B. Then when assertion is true but reason is false, option C. When assertion is false but reason is true, option D. So let's start. Your first question, assertion, SN2 reaction do not proceed with retention of configuration, and reason, SN2 reactions proceed in a single step. Let's analyze this question. See, what is SN2 reaction, students? It is a nucleophilic type of reaction. So I am going to take this halide. Okay, so when you treat with sodium hydroxide, it goes via through this transition state in which the incoming group and the leaving group has not been or still bonded to the carbon, okay, through this transition state. Okay, so the next step you will see that the product has been the exact opposite in configuration to this. See, here the leaving group is attached to the right hand side of this carbon and the incoming nucleophile is in the left side. If you start with R, you will get S. So this we call it as inversion in configuration, okay. So the assertion is true. The SN2 reaction do not proceed with retention in configuration. Yes, retention means if you start with R, the product will also be R. That is retention, okay. So here it is inversion in configuration. If it rotates a plane polarized light in clockwise direction, this will rotate the plane polarized light in anti-clockwise direction. So what is the reasoning? SN2 reactions proceed in a single step. This is also true, but is that a proper explanation of this assertion? Okay, so it is not. Both assertion and reasoning are true, but reason is not the proper explanation of the assertion. So option B. Okay, students. So you have to analyze in a stepwise manner. That's all. Okay. So now the second question. Tertiary alkyl halides show high reactivity towards SN1 reaction. Yes, true, very true. We saw that what is the order? Tertiary, secondary and then primary. Okay. So if you have any tertiary halide like this, okay, tertiary halide like this, what happens here when you treat with hydroxyl group? So since due to steric hindrance, the leaving group leaves first. The leaving groups leaves first, giving a stable carbocation. Stability is very much important here. And then the hydroxyl group groups attaches to the carbocation in two different fashion. From the upwards fashion and the downwards fashion, always you will end up with a mixture of compounds, okay, one with retention in configuration and one with inversion in configuration, okay. So this we call it as racemic mixture. This is 50 and this is 50. It takes place in a single step. Tertiary carbocation has more stability. Yes, it is due to this stability of carbocation the tertiary alkyl halides show high reactivity in SN reaction. So assertion and reasoning both are true, and reason is the proper explanation of the assertion. So you have to choose option A. Okay. So next question, assertion. See, this is a double bond, okay. An alkene reacts with chlorine at a higher temperature to give this compound. See, watch this carefully, where the chlorine has been attached to this methyl, okay. You have removed one hydrogen here and one chlorine here, and the byproduct is HCl. See, and what is the reason? At high temperature, chlorine dissociates into chlorine free radicals, which bring about allylic substitution. This is very, very true. See, if if you predict an ionic mechanism, like if it undergoes, dissociate like this ionic mechanism, what would be the product, students? The reaction would have taken place at the double bond and you would have ended with a divinyl chloride, but this is not the product. So the ionic mechanism, no ionic mechanism here the radical mechanism has taken place. What it is? See, the chlorine has dissociated. See, this kind of dissociation takes place when one chlorine goes with 2 electrons and leaving behind this chlorine as electrophile, and this is mutual sharing. You take 1 electron, I take 1 electron. So this is 2 chlorine radicals. So obviously this is a radical mechanism has taken place, which reacted in the first step it will abstract the hydrogen radical from here. So hydrogen radical from here. So this is stabilized because of this double bond. This is stabilized, forming HCl, and one more Cl radical will go and attack here, giving rise to this product. So both are true. The option is A. Assertion: nucleophilic substitution reaction is in an optically active alkyl halide gives a mixture of enantiomers. The reaction occurs through SN1 mechanism. Yes, just before we saw that in an SN1 mechanism, in which mechanism you will get the racemization, a mixture of products? Only in SN1 mechanism, isn't it? So the reaction occurs through SN1 mechanism. Yes, the nucleophilic is optically in an optically active alkyl halide gives a mixture of enantiomers. So only through SN1 mechanism you will get 50:50 racemic mixture. So both are correct and it is a proper explanation. So option A. The primary allyl halides show higher reactivity in SN1 reactions than other primary halides. See, what is primary halides, students? For example, I am going to take this one. This is a primary halide. I am going to take a primary halide which is allylic in nature. So this obviously will undergo reaction through SN2 mechanism, but this one will undergo through SN1 mechanism because its carbocation will be stabilized. In SN1 mechanism there will be a formation of carbocation, and this carbocation will be stabilized through the allylic resonance. Through this resonance, the carbocation, in SN1 mechanism, the stability of the carbocation is more important. Stability of carbocation is more important. Is more important. So you can see that this one, a plain primary halide, will go nucleophilic substitution through SN2 mechanism, whereas the allylic chloride through SN1 mechanism because of this resonance. The intermediate carbocation is stabilized by resonance. So both are correct, and reason is the proper explanation of this one. So it's very easy, students. You have to analyze and do it patiently. That's all. Hydrolysis of 2-bromo-octane. What is 2-bromo-octane? Octane refers there are 8 carbon. So in 2 position there is a bromose. The rest of the things 1 2 3 4 5 6 7 8. See how much big it is. See, even though this is a secondary in nature, due to this very bulky group, it cannot attain this crowded transition state. This crowded transition state is not possible because of this crowdedness. 1 2 3 4 5 times. So even though it is a secondary, this crowdedness is expected in which mechanism? SN2 mechanism. So this will not be followed, and the nucleophilic substitution takes place through SN1 mechanism. So this reaction proceeds through the formation of a carbocation. In which mechanism formation of carbocation takes place? In SN1 mechanism. So So the reason is correct. The hydrolysis of 2-bromo-octane proceeds with inversion of configuration. Inversion of configuration where it takes place in SN2 mechanism. But I told you, because of this steric hindrance, it will not follow SN2 mechanism. So assertion is wrong. Your assertion is wrong and your reason is correct. So which option? Option D. Okay, students. Now, the tertiary butyl bromide undergoes Wurtz reaction to give. Okay, so what is Wurtz reaction, students? If you take any R aldehyde and you treat with sodium, you will end up with double the alkyl groups. Okay, so you started with R and you have got 2R here. Okay, so similarly, what is your tertiary butyl? So this is your tertiary butyl. Okay, so here I am going to treat with sodium. So what happens? What will be the product? I am not going to repeat. So another molecule here. So what happens? Two molecules of tertiary butyl group will attach. Okay, you will end up with double the group. So this is what? This is 2,2,3,3 tetramethyl butane. Correct. Okay, so in Wurtz reaction, alkyl halides react with sodium in dry ether to give hydrocarbons double the number of carbon atoms present. This is also correct, and this is the proper explanation of this one. So option A. Okay, so here I started with 4 and I ended with 8. Okay, so that is Wurtz reaction. So this is the indication, students. Whenever the carbon atoms gets double, you must think of Wurtz reaction. Then phosphorus chloride, tri or pentachloride, or preferred over thionyl chloride for the preparation of alkyl chlorides from alcohols. Phosphorus chlorides give pure alkyl halides. See, phosphorus chloride are not preferred, even though from alcohol. Okay, PCl3 gives what? The corresponding RCl. Okay, plus H3PO3 here. So when you do the same reaction PCl5, you will get RCl plus what you will get? You will get HCl plus POCl3 here. But when you do with SOCl2, you will get RCl plus SO2 plus HCl. See, this is a beautiful explanation is there. See here, even though all the RCLs are very pure, no doubt about it, but this reaction is preferred over these two reactions. Why? Because after performing this reaction, this is also liquid. The separation becomes very tough here, and this is gaseous in nature and this is liquid, and this is also liquid. Here also you can, it's a tedious procedure to separate here, but see, both are gaseous in nature and it will go in atmosphere and you will get 100% no separation. For comfortability, even though all RCl are pure, alkyl halides are pure, we prefer this method due to this reason. Okay, so the assertion is not true. The phosphorus chloride gives pure alkyl. This is true. So the option D. Okay. So your next question. Assertion: presence of nitro group at ortho and para position increases the reactivity of haloarenes towards nucleophilic substitution. The nitro group, being an electron withdrawing group, decreases electron density over the benzene ring. Okay, so the option is A. I tell you why. See here, when you take a plain chlorobenzene, you cannot replace this. With OH easily, because as we know that this chlorine having lone pair electrons would be involved in resonance, and it has a double bond character. It involves a double bond character, which makes the nucleophile to enter becomes very impossible, becomes difficult. But when your chlorobenzene is substituted with, okay, for only one nitro group I'm going to show. Okay, one nitro group I'm going to show when a powerful electron withdrawing group. So what happens here? It facilitates the OH minus here before the chlorine leaves itself. Okay, so the nucleophile, it's a powerful electron withdrawing group, so it attracts a nucleophile here. Okay, it dominance is on ortho and para position. So para position, the nucleophile first enters. Okay, and through resonance it stabilizes the the negative charge. It takes that negative charge. Then what happens when it comes back? Okay, so the chlorine goes away. Why the chlorine goes away? Because carbon oxygen bond is comparatively stronger than carbon chlorine bond. Okay, so by this way the nitro group facilitates a nucleophilic substitution reaction. Okay, without in unsubstituted nitro it is impossible. Okay, so both are correct and the option is A. So in monohaloarenes, further electrophilic substitution occurs at ortho and para position. Halogen atom is a ring deactivated. Both are correct statement, but this is not the proper explanation of this one. I'll tell you why. See, your chlorine group has two effects. What is that? A powerful minus I effect which withdraws electrons through single bond plus R effect. Okay, here what happens is the plus I effect dominates here. But your chlorine has lone pairs, isn't it? Your chlorine has 3 lone pairs, but due to its strong electronegativity, it will not donate much. It has 3 lone pairs. Oxygen has 2 lone pairs. It makes the benzene ring very rich, but even though it has 3 lone pairs, due to its minus I effect, it will not give. So whenever you do any reaction, you will get only the mono substitute, either ortho or para. Okay, not a this is your electrophile, isn't it? So electrophile. Okay, either this or that. Okay, and and that too in a very small amount. Okay, so you will get only the ortho. This is the correct statement. Reason, halogen atom is a ring deactivated, but this is not the proper explanation of this one. Okay, so option B. Assertion. It is difficult to replace chlorine by OH in chlorobenzene in comparison to that of ethane. Yes, carbon chlorine bond in chlorobenzene has a partial double bond character. Both the reason are correct. Option A, it's a perfect explanation as I told you here. The chlorobenzene, the electrons are involved in resonance, so it has a double bond character. Whenever okay, it gets attached to a double bond, in sp2 carbon, sp2 type of carbon, it will be involved in resonance. There will be a double bond character. Okay, this is option A. Then assertion. Alkyl iodides can be prepared by reaction of arenes with iodine in the presence of an oxidizing agent. The oxidizing agent oxidizes iodine to HI. See, I will tell you what. See, any arenes, okay, substituted or unsubstituted, when you treat with iodine, yes, the iodination takes place. Substitution, no, so you will get HI. But what happens? This reaction becomes reversible due to the presence of this HI. So what happens? HI again reacts with this iodobenzene to give back iodine and benzene. Okay, so to stop this, what we have to do? We have to remove this HI. So we are going to use any oxidizing reagent, okay, HNO3 or HiO4, okay, like that. So what happens? Your oxidizing reagent reacts with your HI to give iodine back. So you are increasing the concentration, regenerating iodine from HI. Okay, so the forward reaction according to Leach and Clear principle, you are consuming this HI, turning this to again iodine. This will again involve in this reaction. So the forward reaction, you are moving the forward reaction. Okay, so you can increase the yield of iodobenzene here. Okay, so this is correct statement. The oxidizing agent oxidizes iodine to iodine. See, this is already an oxidized state. Okay, this is reduction actually, so this is wrong. Okay, so the option C. Oxidizing agent oxidizes HI to iodine but not the reverse. So the isomers related to each other as non-superimposable mirror images are called enantiomers. Enantiomers possess identical properties. See, this is A, B, C, D, having 4 types of groups. Okay, if you take this the mirror image, the B will come here. So this is a non-superimposable mirror image. Okay, so the relation between them, we call it as enantiomers. That is true, very true. Both we know that apart from the rotation of the plane polarized light, they have the same physical properties. Apart from the rotation of plane, they only differ in the rotating the plane polarized light. That is the only difference they show. This is also correct, but is this explaining the proper, is that a proper explanation of assertion? No. So option B. Okay, so the racemic mixture containing two enantiomers in equal proportions will have zero optical rotation. Yes, very true, isn't it? See, if your product contains, okay, they are enantiomer, we said. So enantiomer, we said. So if it is R, its mirror image will be what? Its mirror image will be S. This will rotate the plane polarized light in this direction. This will rotate in this. Both get nullified if they are in 50:50 mixture. Okay, one will rotate in this direction, one will rotate in this direction. Both the quantity will get nullified and you will get optically inactive product. Okay, so where you can see the students in SN1 mechanism. Okay, so the product you got from SN1 mechanism is optically inactive. Okay, please recollect. So this we call it as racemization also. Okay, we have to recollect then and there. That is all about organic chemistry. This is because a rotation due to one isomer will be cancelled by the rotation due to the other isomer. So option A, both are correct, and this explains the proper explanation. So then butane 2-ol is a chiral molecule. It has 4 different groups. See, let's see what is butane 2-ol. So butane has 4 carbons, and in the 2 position you will be having a OH group. So this carbon has 4 different groups. Yes, it is optically active. Yes, it's a chiral molecule. So both are correct, and option A. So propane 2-ol is an achiral molecule. Okay, let's see what is propane 2-ol. Propane means 3 carbons. In the 2 position you have an OH. Okay, see, both are same. No, it is not an optical, it is an achiral. It is an achiral molecule. This is correct statement. Carbon is called asymmetric carbon or stereocenter. There is no stereocenter at all. This is false. Okay, so option C. Okay students, I hope you understood something. If you find it worthy, please share with your friends. Okay, and I will soon meet you in my next video, okay, with other set of questions. Thank you.